This slide here now that shows us the hormones that affect bone growth. So what do we mean by hormones affecting the bone growth? So for example here, I'm pretty sure all of you, well, many of you, if not all of you, have heard of vitamin D before. And I'm sure also that many of you have incorporated that vitamin D is actually good for the bones, right? And the reason for that is actually why. So when we talk about the vitamin D, so this is going to be formed in the skin when exposed to sunlight. So every time that we're outside and our skin is being exposed to sunlight, we are actually forming or making vitamin D via our skin. This is converted to a hormone that is necessary for absorption of calcium from the food. So meaning the calcium that is literally going to be directly associated with bone strength and bone growth, this is necessary to be absorbed from our diet. And in order for calcium to be absorbed, we need vitamin D. So what do we mean by that? So if you have noticed before that milk, so when you purchase milk, it's always going to be with vitamin D, right? Or nowadays also there are other drinks out there such as orange juice, like some OJ also, these are now going to be with vitamin D as well. So the vitamin D here, this is basically added to the milk or the orange juice that we are drinking so that it will help us absorb the calcium from the milk, for example, calcium from other food that we also consume from our diet. So now what happens when you are low in vitamin D? So people with low in vitamin D are now going to suffer what is known as rickets. And this is especially in children. So low vitamin D levels in children will now lead to what is known as rickets. And what is rickets? This is bone deformities, including bone long bones, meaning their lower extremities would look like a bow, right? So like this. So this would be the right side and the left side, and now you have the trunk up here. So this would be the bow-legged. So this is known as rickets, and this is due to low in vitamin D. The other hormone here that is necessary for our bone growth is known as growth hormone. This is going to now stimulate bone growth. So this growth hormone here needed concurrent action of thyroid hormone to stimulate metabolism. So what do we mean by that? In order for in order for growth hormone to do its job properly, you need thyroid hormone at the same time. So what happens when growth hormones becomes too much, right, or too little, for instance? So let's first take a look at in childhood. So if you have too little growth hormones, then it will now lead to known as your dwarfism. If they catch this early enough, when the epiphyseal plate is still open, so remember the epiphyseal plate? So when the epiphyseal plate is still open and they catch that this individual, this child, is not producing enough growth hormones, all they have to do is basically inject them with growth hormones, and they will now grow to a normal height. However, if the epiphyseal plate is already closed, then unfortunately they are now going to remain as dwarfs. So that is your growth hormone and lacking during childhood. However, the opposite of that is you have too much, right? Too much growth hormones in childhood. Okay, childhood because of the epiphyseal plate. So I'll put here epiphyseal plate, okay? It's still open, of course, right? This is now going to elongate. So let's say this is the epiphyseal plate over here. Now the bone is going to elongate. So when there's too much of these, now this is now going to result in known as gigantism. So excess growth hormone in childhood results in gigantism. Too little growth hormone in childhood results in dwarfism. An example about gigantism here is in the past they used to have this the wax museum in Pier 39, right, in San Francisco. They used to have this huge person, a wax model of a person, on the entrance, and it's like 8'9" or something like that. And that was actually the height of a real individual. That's because when he was a child, he had too much growth hormone being produced. So the next one here is what happens when the epiphyseal plate becomes epiphyseal line, meaning it has now closed, right? So epiphyseal plate now becomes epiphyseal line, and if this is still going to be producing too much growth hormone in adults, then it will lead to what is known as acromegaly. And an example of that is if you watch wrestling before, when Andre the Giant was still very active, yes, he does have acromegaly. So that's what happens over here. So excessive growth bones in hands and feet. Oftentimes what happens is the individual does not notice this. But as time goes on, if the individual wears hat, for example, the hat seems to become smaller. Their shoes seems to become smaller, right? So as time goes on, their feet, the bones in their feet enlarges, and now they can no longer wear shoes. Well, they can, but they now have to get a larger size. So that's what happened over here. But for individual, again, who have not seen that person for a long time, they would notice that there's something different in their face, in their hands, and so on and so forth. So that is the growth hormones. The other hormone here is your sex hormones, increases growth during adolescence. So such as testosterone, for example, right? Testosterone in the male, yes, this is going to increase growth during adolescence period. So those are the hormones that affect our bone growth. Next slide here shows us bone remodeling and calcium homeostasis. So what do we mean by that? So when the bone is made, basically, right? So when the bone is calcified, they are going to be maintained so that they are going to be kept strong, basically. If there's no maintenance, then we're going to have a problem. So how do we maintain our bone to be strong? So this is now going to fall under calcium homeostasis. If blood calcium rises, okay, so too much calcium in the blood. So after you have consumed diet with rich in calcium, for example, some of the excess is going to be deposited in bones. Okay, so calcium is now going to be deposited in the bones. So that's the excess one over here. However, if the blood calcium drops, that's because you don't have enough calcium in your diet. Then the calcium that was deposited in bones is then going to be removed. So calcium is then removed from bones to bring it back up to normal. The reason for this is because calcium is very important in the body, such as muscle contraction, which we'll talk about later on, and also in hemostasis. So remember, try to recall when we were talking about hemostasis as well. So that is the role of your calcium with regards to the bone. Now, how is the calcium going to be deposited in the bone, and how is the calcium going to be removed from the bones? So now we need these hormones over here. So parathyroid hormone, okay? This parathyroid hormone over here comes from the parathyroid gland. We'll talk about this one later on as well. So this is going to stimulate this osteoclast. Just remember the osteoclast. These are the bone destroying cells. So they are now going to stimulate the osteoclasts to dissolve bones, okay? Right here. Promotes calcium absorption in the small intestines and kidneys, ultimately increasing the blood calcium level. So three functions of the parathyroid hormones. So it will destroy the bone, or it will dissolve the bone, okay, releasing calcium, right, in the bloodstream. So calcium in the bloodstream, right? So that's the first one over there. The other one over here, it's now going to promote absorption of calcium in the small intestines. So now you have calcium being absorbed from the small intestines, right? Again, dumping that calcium back into the bloodstream. The other one over here is kidneys. So parathyroid hormones is now also going to, okay, have the kidneys reabsorb more of the calcium. So all these effects right here leads to calcium reabsorption going into the bloodstream and then increasing this blood calcium level. So that's your parathyroid hormone. So parathyroid hormone helps destroy the bones, or basically because it activates the osteoclast to dissolve the bone. The counterpart of the parathyroid hormone over here is your calcitonin. So basically calcitonin, this comes from the thyroid gland. It has the opposite effects of PTH. What do you mean by that? It is now going to reabsorb calcium from the bloodstream, the kidneys, right? And also from our diet to be deposited into the bone. So calcitonin, okay, will reabsorb calcium, okay, from these systems over here, and then deposit in bones. So that is the calcitonin. So parathyroid hormone and calcitonin have the opposite effect of each other. Vitamin D, we already mentioned this one here. This is for absorption of calcium from your digestive tract. So the calcium from our diet is going to be absorbed from our digestive tract with the help of vitamin D. The last one here on our slide is estrogen. It increases the number of osteoblasts. So osteoblasts, if this is the bone destroying cells, this is now the opposite of that. Osteoblast, this is now going to promote building of the bones. So estrogen increases the number of osteoblasts, therefore it increases the bone remodeling, or it increases bone growth. Reduction of estrogen in older women when they reach menopause, right? So when they reach menopause, now they no longer have estrogen, or they have a greatly reduced amount of estrogen in their system, then now that could lead to osteoporosis. Why? Because they no longer have the osteoblast that is maintaining the bone health. All right, so that is the bone remodeling and calcium homeostasis here. Next slide here shows us an example of an osteoporosis. So this is one of the bone diseases. When we talk about osteoporosis, the bones get weakened due to decreased in bone mass. Remember, osteoporosis, calcium down, right? So that's what we have over here. Skeletal mass increases until the age of 30. Okay, once we reach this age, calcium mass, guess what? It starts to decline. After that, there is an equal rate of formation and breakdown of bone mass until the age of 50. So 30 all the way up to 50, it's equal, basically, right? So equal rate of formation and breakdown of bone. So they're balanced at this age. What happens next? After the age of 50, then reabsorption begins, okay? Exceeding the formation of bones, therefore the total bone mass is now going to slowly decrease. So here is a picture of a normal bone right here under the microscope. And look at the osteoporosis. See the difference, right? See this lattice right over here? Thick lattice. This one is now virtually none, gone, right? So that is your osteoporosis example right over here. Risk factors of osteoporosis: women, white or Asian, right? Thin, family history, and so on and so forth. So these are all the risk factors of developing your osteoporosis. Next slide here. So this part here is another abnormalities of bones, or basically traumas that can happen in bones. So this is now specifically bone fractures. So what happens here? We have different types of bone fractures. So what are these different parts of it? Different types over here. Complete. So complete, okay, complete fractures. That means that the bone is broken clear through and through, right? So the bone is broken clear through and through. That is known as your complete fracture. What else do we have here? If incomplete, the bone is not separated into two parts, basically, right? So incomplete. We have simple and compound. So simple does not pierce the skin, compound does pierce the skin. What else do we have here? We have impacted, and we also have spiral. Okay, so impacted, broken ends are wedged, okay, into each other. Spiral, the break is ragged due to twisting of the bone. So let's see the figures here. What do they actually would look like? So here is now an example of our complete versus incomplete. So these would be all complete. Remember, when we say complete, bones is broken clear through and through. So as you can see, these are clear through and through. Simple, okay, compound right here. So that's what we have right over here. So simple, when the bone does not pierce the skin, so this would be considered simple right here, simple right here, simple right here. You guys get the idea. So this one right over here, of all this in this figure, there is only one compound fracture here, and that's this one right over here. Okay. So another term for compound fracture would be open fracture. Another term for simple would be closed right here. Okay. So that's what we have in our figure right over here. So specifically now, what are these other types of fractures here? We have transverse. So this is kind of like the impacted, broken ends are wedged into each other, right? So, but the transverse, because the broken part is just literally horizontally located. So transverse. Spiral, right? The twisting right over here. Okay. Comminuted, another form of fracture here. That's when you have little pieces. So think of it as shattered bone. Okay. So compacted here is now similar to this transverse over here, except the way that it's broken up right here. So when the two are wedged to each other right over here. Okay. So this one transverse, not wedged to each other, but this one here now specifically they try to depict that this bone right here is wedged with each other from the broken part. Green stick fracture over here, this is common in children and it's partial only. So only one side would be broken, but the other side is still intact right there. And how do they treat this? Basically, if this happens in children, they will need to break it through and through. They need to do that because if they don't, this is not going to heal well. Okay. The last one over here is oblique. So now you can see it as in the diagonal right over here. So those are the different types of fractures. So what happens now? So when a person is have a fracture, what happens to these fractures? How does this fracture heal? Next slide over here shows us the steps of actual bone repair. So what are the steps of this actual bone repair? So first, what forms is what is known as hematoma. So this not only happens in bone, but let's say you wedge you're trying to catch a ball and you wedge your finger against the ball and then your fingernails, right? Underneath it, there's a blood forming there. That's a hematoma. That's a type of hematoma right there. So in a fracture, first, a hematoma will form where the fracture is, right over here. So forms 6 to 8 hours after the fracture. Okay, so blood clot between the broken bones so that blood will not blood loss is minimized right over here. So the bleeding would stop. So that's your hematoma right there. So here is the periosteum. Try to recall what those are. It's been broken up right over here as well. And of course, now you have these two bones right over there that is broken. Next one here is the fibrocartilaginous callus will now form. So 3 weeks time, now you have this fibrocartilaginous callus, fibrocartilage callus between the broken bones. So now the blood right over here, the hematoma, is now replaced by this fibrocartilaginous callus. So think of it as a cartilage basically, right? So this is your cartilage right here. Remember when we talk about the bone formation, that oftentimes bones are formed from cartilage first, becoming the framework, and then it's going to be calcified. So now that's what's happening right over here. After that, now you have the bony callus. So bony callus 3 to 4 months after. So now you have the bony callus right over here. So the cartilage is now replaced with bones. How so? By the calcium being deposited in it. So that's what is shown right over here. Cartilaginous callus now turns into bone. And then finally, the last one is remodeling. So let's go ahead now and repair the inside. Osteoblast, build new compact bone. There goes the new compact bone. So this part right over here, new compact bone. Okay? New compact bone at the periphery. Osteoclasts absorb the spongy bone. So this would be the spongy bone initially right over here, right? So now you have the osteoclast destroying this right over here or absorbing it, right? Creating a new medullary cavity. So now we have the new medullary cavity right over here. So once again, this at least would take 3 to 4 months for this to actually heal right here. So that's why in sports injury, for example, if it's a broken bone, oftentimes, depending on the sport that they play and the part of the type of bone that is broken, yep, it would take them at least 3 to 4 months out of the game before they can return again. Right? So that's what they try to achieve over here. So that is our bone remodeling. Next slide over here shows us the checkpoint. So this is talking about the epiphyseal plate. So what does epiphyseal plate become in adult? So try to recall that. So what does epiphyseal plate become in adult? All right, so that ends our lecture here. Okay, and I will continue this in our next series of lecture in the next topic.